Can you all see my screen?
Yes, we can.
Yes.
Yeah, should be fine.
Okay.
So yeah, thank you, Irvin. Good morning, everyone. We're indeed delighted to hold this presentation here today as part actually of the RAIN webinar. As you can see, we are actually a team from 5 different institutions. Specifically today, there will be Stuart Fowle from Capgemini, previously Altron. There will be David Rees from the UK Atomic Energy Authority. There will be Irvin Lopez from University of Manchester. There will be Dr. Lee from the Nuclear AMRC. Well, we certainly have also the University of Bristol as part of the overall team of this kind of project. ICON Plus is pretty much the idea of introducing a wireless control infrastructure into nuclear assets, into nuclear energy systems, in particular for control and control communication. And in that respect, actually, Irvin, can you go to the next slide? We will be talking here about the history of ICON, introducing actually control communication, control infrastructure into actually wireless control infrastructure into nuclear assets. Particularly also, we would like to provide you actually with the value of the next instantiation, ICON Plus, into actually, obviously, control communication, wireless control communication into nuclear assets, the actual technical challenges, and also the technical aspects and the steps towards it. And as you see, we are a great team. And specifically, our team is interested actually to present this idea here to you today. We started off with a feasibility study, actually with a viable feasibility study, but we would like to talk to possible actually people involved actually in nuclear assets, in nuclear stakeholders, possible sponsors, possible supporters actually of this kind of project, and would like to see and disseminate actually our idea actually towards the nuclear community, and also in general also the harsh actually condition community. In that sense, Irvin, next slide please. We would like to introduce at first to you actually the idea of ICON. ICON was initially an Innovate UK funded project under the lead actually of Altron, now Capgemini, under the lead of Diane Daw, who has been unwell recently and therefore cannot join us, so we wish her all well. And in that sense also Moltex Energy, a small modular reactor producer, has been part of that initial projects, and the University of Bristol, my previous affiliation, and a team there has been part of it. Moltex Energy actually produces actually small modular reactors. They have been UK government supported, but they're working now with the nuclear regulators in Canada to build then small modular reactors. And clearly as a modular reactor, they were searching actually also for wireless control infrastructure being truly modular to be able to build their truly modular reactors. The benefit actually of wireless control infrastructure is clearly you would eliminate actually physical power cabling, physical harnesses in actually the reactor, around the reactor, reduce in that sense maintenance and cost. At the same time, you actually introduce faster deployment, greater flexibility for deployment in hard to reach areas. You certainly also would reduce actually and eliminate actually radiation dosage on human personnel for greater safety. And if you actually understand also wireless communication well, then actually you understand also that you can introduce actually strong levels of cyber security and securely communicate actually control and communication across actually that kind of infrastructure. And clearly, having actually small control units, you're able actually to remotely power, even use energy scavenging actually to power actually any kind of control unit in this kind of system. Irvin, can you next slide, please? In that sense, actually, our feasibility structure came up actually with a certain coherent set of ideas. We would be exploiting actually the IEEE 802.154E protocol within actually the containment above the reactor, the refueling containment, and in that sense, we actually also tested actually for robust performance, for data loss and delay. We actually also looked at radiation-hardened devices, but most importantly, also we looked actually at a safety analysis of our overall structure. And that was carried out by our colleagues at Capgemini and by nuclear safety experts there, and was actually checked then also by the Office of Nuclear Regulations. And they found that our path towards actually augmenting Catalyst 3 control systems with wireless control communication structure would be actually indeed very feasible, even though they agreed there would be actually a lot of work still to be done, but they actually thought our concept was indeed viable going forward actually on this kind of idea. And in that sense, actually, I would like to hand over now to Dr. Li, who will be talking now about possible use cases in that kind actually of environment. Erwin?
Thanks, Guido. As Guido just mentioned, the feasibility study for ICON already in the SMR and AMR domains. So this is suggested, and so the wireless control technologies will bring the benefit for the next generation advanced reactors. Also, this technology can use in the mining industry as well. And so the wireless technology can help the mining industries to overcome communication barriers and in the harsh environmental. Also, they can operate the unmanned vehicles for improve the safeties and remote conditions. If you're looking for the current operation fleet in the large nuclear power plant, some of nuclear power plant in the US already adapt some of the wireless control technologies in the turbine island and the balance of plant. So mainly controls the solenoid valve and the pumps. Move to the D&D, then you can see the lot of robotics operate in the dismantling and decommissioning. So particularly in the decommissioning, and if you come from UK, you're aware about the NDA and Sellafield deploy a lot of unmanned vehicles and it's remote operation vehicles and in the pond as well in the storage facilities to improve the safeties, also bring the efficiencies of product activities. It's quite promising. Currently, the UK looking for the GDF, the geographical disposal facilities. As you can see, there's a lot of opportunities for this technology to deploy in that facility as well. For example, you can use the remote controlled robot and remote handling equipment controlled by wirelessly and overcome some of the communications and the condition monitoring barriers. So next slide, please.
So thank you, Lee. Moving on from the nuclear use case that Lee's talked about, we're looking towards the use case for a commercially viable fusion reactor as we're working on these designs. And in order to make the fusion reactor commercially viable, we need a fast and efficient way of servicing that reactor, which reduces the shutdown times to a minimum. So we're not waiting for the reactor to cool down or the levels to go to benign levels. So the operating environment of our remote handling and robotic equipment is going to be a harsh environment. It's going to be elevated temperatures, high residual magnetic fields, and have to endure high levels of radiation. The sort of task that the remote handling equipment has to do in a fusion reactor is to move large inner wall components of the vessel, like the blanket modules and the diverter cassettes. And in order to do that, there has to be cutting and re-welding of cooling pipes and other infrastructure in very tight constrained volumes close to the reactor center. So typically, or traditionally, in an experiment such as JET that we have here, the remote handling equipment is tethered by very long cables where we have remoted the sensitive electronics away from the hot side, you know, maybe 150 to 200 meters away. But that might not be possible in a commercial fusion reactor. So we are significantly restricted in space and volume, and we're facing those kind of challenges in the design of the remote handling equipment for ITER. So wireless technology could be utilized to allow the remoting of these components and reduce the need for so much tethered cables. So other advantages we're looking at for fusion is the reduction of electrical noise and other EMC issues that you get with running power and data cables in close proximity, elimination of signal degradation and loss down the long cables, and the multiple connections and junctions that you have down the long cables. And we certainly suffer from that problem at JET at the moment. One other use case we're looking at is the cask systems that will deliver the remote handling equipment from the hot cell to the ports of the reactor vessel, and then remove the spent components and return that to the hot cell. So we're looking at wireless technology for this sort of navigation and control of those cask systems as well. So next slide, Owen. So I've just mentioned the environment that we're talking about, but these are sort of the figures that we're looking at, and there's a lot of crossover with the nuclear use case. We're talking about high radiation in excess of 1 megagray total dose, 120 grays per hour, 300 grays per hour, depending on where you are, high residual electromagnetic fields, and also elevated temperatures, so 50 to 120 degrees. So that's the environment, and Erwin is going to talk to us about the communication challenges.
Yes, thank you, David. Yes, so inside our work, we began knowing about the challenges and the technical challenges behind ICON Plus, and besides what the environment provides, which is a low survivability of any kit that you want to put into these hot cells or the harsh environments. The environment itself also hinders communication, or basically generates interference. This is seen not only by the environmental variables such as temperature, radiation, EMI, so on and so forth, but also the layout, the obstacles around the signal propagation. So we see both geometry and material being affecting this signal. So it's something that we need to consider. And also, of course, inside these environments, there can be, and usually are, moving targets that cause other additional disruptions. And when we talk about disruptions, they are not critical or that they break the link channel, but we need to consider them in order to do appropriate design. Particularly because we talk about safety in these cases, and these links need to be as good or even, well, at least as good as a wire connection, meaning that we need to have high availability on the connection or the links, meaning that it also implies we have some type of mesh of networks. So we have many signals, many ways where the signal can lead this appropriate way. In addition to these challenges, we also consider application-driven challenges, as each application drives the performance metrics. What I mean by this is that ICON started talking about control signals, which means sensing the environment and sending control inputs. And this can be translated into normal sensor signals like temperature, but also video is something that is necessary in many of these applications in the nuclear industry. So we divide this into two: control signals and video signals, the latter being more similar to what we are doing at the moment through Zoom. And this changes dramatically what we consider a performance metric, where in video applications, we need a lot of bandwidth with relatively small delays of less than 100 milliseconds. But for control purposes, the bandwidth is not that crucial. However, we do need to create deterministic delays in applications for less than 30 milliseconds, which in itself is quite challenging in this type of environments. And in addition, for all this to be created, we need accurate timings, because all these protocols are based on real accurate timings, which means that the clocks that we use need to be also very precise. However, in harsh environments, one of the first things that go out of the window are clocks and this type of silicium. So these are some of the challenges that we know that we're facing. And inside the ICON Plus project, what we're trying to create is to push forward our technology readiness level from early designs to some prototyping, maybe around servo control of a robot, meaning that we want to create the infrastructure for this wireless control, meaning that we can connect several pieces of servo control kit or parts of the robot, and we can test how we could both model the process but also control these robotic devices. Of course, starting from the basics of a maintenance application in a harsh environment. And again, as you would imagine, using COT devices, which we already know that has many challenges, which I will explain forward in the next slide. So to push ICON Plus to the next TRL level, some prototype architecture that we're describing are what you see here on the screen, which will entail that in the left side, we have this maintenance robotic device, which most likely is either mobile or a robotic manipulator or gripper. And inside this, which is quite complex and high and large, we would create our ICON Plus devices, which will be nodes, which connect between each other through wireless connection. And they are the ones who are doing the signaling and the processing and getting the signals from a wireless relay connected to the control room where the operators and the controllers would be. Basically, this is a traditional architecture from here to here, with all of this part being wireless. In that regard, how we see this being positioned in, let's say, close to real applications, it's based on where or how close to the reactor vessel they are positioned, this kit. Because the closer you are, as you might imagine, the hard condition gets harder and harder, meaning that we have a divided approach where we know that COT wireless devices have an application and serve a purpose. And in order to make them more reliable and to make their survivability higher, as you might imagine, two approaches that we are considering is the classical shielding of these devices, plus the redesigning and reuse of different components of RAD hardened or RAD enabled components for the wireless PCB, basically, plus the shielding. So it's this compounded approach, which of course, as you might imagine, comes with some challenges and cost. However, the initial prototype will be positioned in applications and use cases around this area, where a harsh environment might be possible. It is there. However, we can showcase some of the applications and the power of the ICON Plus project as we do a maintenance application. Now I'll hand over to my colleague Stuart, so he can talk to you about the pathway towards ICON Plus. Stuart?
For me, sorry. Okay, so to summarize the technical aspects, what we're looking to do in ICON Plus is to produce a future-proof design that's aimed at deployment. So that means establishing the control task requirements and the video requirements, actually, and looking at performance objectives such as the latency, jitter, bandwidth, etc. To scope the current technologies, looking at COTS. Primarily the various guises, and take account of the security considerations and available wireless technologies. To understand the environment that they'll be operating in, take account of how dimensions affect things, materials, radiation, EMI, etc. in the harsh environment, to model that environment and the effect of that on the comms and control all the comms, so take account of things like packet and connection loss, and to be able to replicate those effects in a computer model so that we can make use of that for design and prototyping purposes. So that then lets us test and validate the performance and the safety aspects of ICON Plus in a robotic testing environment. And really what we're looking to do is to produce both hardware solution and an architecture that's reached the TRL4 stage, so demo in a lab environment of the prototype wireless network. With a set of tangible deliverables, we will have a COTS-based wireless transceiver system that can be then taken on and tested in harsh environment within well-defined experimental setups like at Dalton and in temperature chambers that's been integrated into existing robotics control system. So it's actually a real demo application over the top of the wireless system itself. So that gives us then this proof of concept of the behavior of specific control loops in the robotic control system, and we can explore how, demonstrate how that reacts subject to the selective communication of faults caused by the environment. And then alongside that, building on ICON 1, we will progress the safety assurance case and also introduce a cyber assurance case, taking account of the fact that we're talking wireless here, so it is potential for cyber attack there. Okay, next slide, please. So really, then this gives us this slide gives us the view of the progression of ICON that we're looking to do. We performed the ICON 1 feasibility study, which produced a technical architecture and identified a safety approval strategy. And then we want to move on to understand the constraints within an active site for wireless COTS and where they can be applied, taking account of what tolerances they have of the harsh environment. We want to particularly look at the wireless video case in the nuclear context that wasn't part of the original ICON 1 study. And when we want to really articulate all the use cases for wireless control within the environment that we're operating in. Building towards the prototype in the lab, in a host environment, that's demonstrating the use case of simulating the harsh environment. And then the final stage is where we actually put that into a controlled harsh environment or a set of harsh environments to demonstrate the actual behavior. So moving from simulated in a lab environment to a represented environment. Okay, next slide, please. Guido?
Yeah, thank you very much. So as you have seen, we have here a very strong team. Particularly actually for this project, we will have also an advisory review board, of which actually Professor Peter Green from the University of Manchester will be part of. He is a specialist in communication, in particular actually for nuclear assets. We have also part of this actually John May from the University of Bristol. He is a specialist in safety, specifically again also for the nuclear sector. And we have also Dr. Lee, being obviously the technical lead at the nuclear AMRC, and Bill Hodgson actually part of Cambridge Consultants. But on the ground, we have people like Kate McLaughlin, who is a very experienced project manager. We have Stuart Fowle, who has been working and delivering for many years industry actually scale actually R&D projects. And myself, actually Guido Herrmann, I've been working on control communication together, for instance, also with Jaguar Land Rover, publishing a monograph with colleagues actually from Jaguar Land Rover and from my team. We have Dr. Irvin Lopez actually being an expert in mechatronics, therefore actually delivering actually the wireless and control part. The integration and testing will be done then actually at the nuclear MRC by Dr. Sunny and Dr. Zhao, who are actually expert in integration. And clearly we have strong experts in the use actually case, Matt Goodliff and David Rees, but who are equally actually very experienced in the creation of recent actually control infrastructure in general, Cortex is possibly now very well known among the community, and therefore advice from them on that side will be equally useful. So our intention of this presentation is today actually indeed to engage with possible actually supporters, sponsors for this kind actually of next step, clearly on a mid and higher TRL level. And we would like to actually see garner actually some further support. Hence, actually, this is the end now of this presentation. We would like to thank you actually for your attention, and we look forward for further questions, obviously now in this part of this presentation. Thank you very much.
Yes, thank you, Guido. Thank you, everyone. If you have any questions, you can just, we have a couple minutes now. Sorry, we went overboard, but please feel free to put them in the chat box, or maybe unmute yourself so you can just ask yourself to the people around you. And we have a question.
There is a timeline for the ICON Plus aims, actually. I mean, we developed actually already a concept, let's say, up to the prototype, actually, let's say, and in that sense, we have that team here, and our timeline was actually then about a year, I think half a year, I think about a year. That was our idea, given actually that we have that kind actually of team actually set up. Well, actually, clearly, I mean, once we go actually to higher TRL levels, actually there will be extra time actually to be set up. Yeah.
Thank you, Guido. Now we have another question. So for everyone who's joining us, William Harwin asks, with regards to control, I understand 6LoWPAN is a slot-based protocol that seems ideal for fixed delay control versus others such as Zigbee. What is the thinking in ICON? Oh, that's an interesting one. Do you want to get it, Guido, or should I?
Yeah, I mean the 802.154e actually pretty much is similar, allowing for actually so-called time division multiple access kind of schemes. So I think that's pretty much what Will actually here is addressing. So there is actually the newest instantiation actually allows for obviously this kind of actually structure. Also channel hopping in addition. There will be obviously on that kind of higher actually level actually of that in the communication stack, actually still some work to be done, but the communication protocol was wisely chosen in that respect. Irvin, do you want to add something on that side yourself?
Yes, just as a small comment. A lot of work has been done in the recent decade about creating protocols and describing how we can make things better in tightly timed environments. However, most of these protocols or specifications, I should call them specifications, they tell you what you should do, but they don't tell you the mechanisms to do that. They don't tell you the minutiae of how one of these timing constrained slot divisions should be done. They just guide you towards something like that. So there's a lot of space there, and still in the community, even the very specific community in that application area, there's still space to explore. That's where we are also not going too much in depth in that part, but how we can connect that with this harsh environment, which affects all these minuscule timing considerations a lot. So that's that sort of work there. I think we are just on time to change to our new second presenter. So if you have any other questions, please put them in the chat box. Everyone's going to be happy to reply. And now I welcome Dr. Joaquin Carrasco from University of Manchester, who's going to talk to us about his project of digital twins. Joaquin, if you please. Thank you.
Hi, everyone. Can you see the slide? Yep, thank you. Okay, so I am going to present the work that we are doing in this topic. This project, Digital Twin-based Bilateral Teleoperation System for Nuclear Application, is a project that we are working at the University of Manchester with Race and with KARI, the Korean Atomic Energy Research Institute. And this project has been funded by the EPSRC in the UK side and NRF in the Korean side. I am going to be speaking about the project itself, the technical progress that we have done over the past year with all the COVID restriction, and this have had some impact, but at the same time, we have been also focused on maybe more theoretical part of the work. And finally, we are presenting hopefully what we are going to do next, involving maybe a little bit more of labs and interaction between the partners. The team at RAISE is given by Salvador, Ipek, and Rob, have been working in RAISE. At the University of Manchester, we have Han-Ling, Hyun, and myself. And in Kerry, we have Hogan and Sunmoon, who have been working there specifically in the area of the nuclear sector, or the nuclear activities that they are developing also in the institute. So the main idea of our project is what we have here in the figure, is trying to actually emulate the environment in the master site. So we are trying to reproduce a digital twin, basically, of the environment, by moving the environment from this side of the communication channel to this side of the communication channel. Sorry for still using slave master terminology. I have been told that I should use how it was, local and remote. So the local part will be this part, the remote part will be that part, and the communication between local and remote is what is generating a lot of problems in terms of delay. What we are trying to see here is if we put the remote environment into the local side of the problem, if we reproduce exactly, or we reproduce with a high fidelity what is happening in the environment, maybe we can avoid the issues that the communication channel is giving me in terms of time delay, in terms of sending forces, and these kind of classical issues that you have when you are doing bilateral teleoperation over the internet. I am going now to speak about the different things that we have been working. In the University of Manchester, we were working over the summer in this kind of demonstration that with a very little training, you can actually control the robot in an intuitive way by using a virtual reality environment. In this particular sample, we basically provide the local site to the University of Edinburgh, and then we just give them around 15 minutes to play a little bit with a demonstration of the system, or with a simulation of the system. And after 15 minutes, the operator was able to do some task with the remote side of the robotic solutions. This communication was done using the Amazon Web Server. So actually what we were doing is sending the signal to London, where I think is the server, and then each of the partners were communicating to the server in London in order to ensure a secure connection over the EduRAM that we have in the universities. In parallel with this work at the University of Manchester, we also have been studying what is happening with or what are the possible solutions that the new technology in reinforcement learning is providing. So can the robot start to understand what the user is doing, and when the performance of the user start to decrease, then can the robot actually take over the user and help the user in a better way? Evidently, this technology is still in a very early days, and if the operator will enjoy that actually the robot is also thinking what is the best thing to do is something that we will need to test with a higher number of humans. In addition, we are also maybe doing a little bit of work in the theoretical side in order to understand how we can improve the speed of convergence of these algorithms that we are using in the reinforcement learning techniques. In RACE, the work has been focused on the transmission of the point cloud. So if we want to transmit point cloud from one side to from the remote side to the local side, it will be nice to understand what is the best way of actually transmitting this point cloud to understand what are the significant part of the scene that we need to transmit, and actually how we can overlay the virtual world that the operator is able to see in the simulation, in the gazebo simulation. So here you can see how the robot, the virtual simulation is already plotting all the robot, but also there is a little bit of data coming from the camera that is evidently part of the robot, and the superposition between both parts is an interesting problem. And what we are trying to do is trying to understand what is the most efficient way of decompressing and compressing and decompressing the point cloud in order to be able to cope with the bandwidth of the communication here. The last part of the project is actually trying to understand what is in the scene, because as you can see here, if you already know that this object is something that you have in your database, if you already know what is this object about, what is the weight and what is the aspect of this object, instead of sending a lot of information with a lot of point cloud that we are sending from here to from this part of the remote environment to this part, if we already understand that this is an object and is within my database, I can summarize the information just by using the information of the pose of the object and the position of the center of mass. This will simplify hugely the transmission of the data by using this semantic information. So the last part of the project is what our colleagues in South Korea are doing. So in this research, initially they take the 3D world and then they transform it into a CAD model. After this, what they have been doing is trying to understand how we can actually map the environment in the best way. So here they have different ways of interacting with the platform that they are using to actually scan the piece that we want to decommission. So they have a haptic joystick, they have a keyboard or a graphical interface to actually interact with the robot that is taking the images of the section of the. In this case, this is kind of a simulation of a nuclear reactor. So trying to understand what is happening there and what are the different components in the nuclear reactor. In the following part, what they are trying to do is a classification, because they have the CAD model of the nuclear reactor, trying to understand what is each piece in the image, so they can now decide where they are going to cut the different part, or from the little information that you get in your point cloud, actually trying to understand in which part of the reactor you are going to be, and they are using a deep neural network to produce a classification of the different components there. And finally, the last step that they have been trying to do is trying to merge all the different images and trying to actually produce a point cloud segmentation. As commented previously, then you replace, if you are able to understand each part of your point cloud, you can, instead of sending to the local part a lot of information with each point of the point cloud, you can actually summarize your information and provide a semantic information of the scene, and help in the speed of the communication between the remote site and the master, and the local site. So what we are going to do in the next year, after this year where we have been developing this intuitive virtual reality teleoperation architecture, we have been trying to actually to see what is the efficient way of transmitting point cloud between the local site and the remote site. We have been trying to actually understand how reinforcement learning can help with this problem, in order to actually to produce a simulation of the environment. Our colleagues have been trying to classify what is in the XM, providing a little bit of information about the different components, because we are assuming that we will have a CAD model of the environment, or at least a CAD model of part of the environment. And the part where we don't have a CAD model, actually we will try to classify, or we will try to produce a CAD model from the 3D point from the cloud point directly. With this information, now in the next year, we are planning to actually to combine the three parts of the work by producing a bilateral teleoperation, hopefully between different countries once we have done the setup. And we are trying to see how we can involve the three partners in the problem. Maybe one of the partners keep the CAD model in their database due to privacy issues or whatever, and then they just provide semantic information instead of providing the full description of the environment. What they can do then is that we can run the classification on the cloud due to the current technology that we are getting there, and then the other two partners are just producing the remote site and the local site in the bilateral teleoperation. I think with this I conclude my presentation. Thank you very much for your attention. Han Lin is also here with me, so he can answer difficult questions that I will not be able to answer. And if you want to contact us, please feel free to drop us an email.
Great, thank you, Joaquin. Yes, please, if anyone has any questions for Joaquin and the Digital Twin project, please go ahead. I see there's one question from Osen.
Sorry, let me open the chat just a second.
Yes.
So the time delay over the internet is not fixed. When you do it between two different universities using EduRAM, the time delay, the normal one, the two ways is around 50 milliseconds, but it can go, it's not fixed. It changes with the use of the internet, and it can go up to 200 milliseconds, 300 milliseconds in the worst case. What we have been also trying to see is if actually this can provide some information to the controller, so the controller is more aggressive when the internet is free to provide data quickly, and then when the network, because it's a public network, is busy, then our controller should work in a shorter bandwidth. No, evidently, if you don't change if you assume that the communication will be 50 milliseconds, and then you tune your controller for this 50 millisecond kind of standard performance, once you have worse delays, the controller can be significantly, or the performance of the controller can be significantly reduced.
Thank you, Joaquin. Any other questions? Oh, hi, John.
Yep.
Hi. Hello, John May, Bristol University. I just wondered how important the accuracy of your digital twin was. is that an issue that you worry about, or?
I mean, we are trying to see what we can provide to the controllers right now. So we are trying to see how we can represent the contact interaction between the robot and the physical part. At the end of the day, the human just needs to get the feeling. You don't need to know exactly what is going to be the exact force. You just need to get a feeling that you are touching something and you are able to hold it, no? So actually the precision is not significant in terms of the force that you are sending to the other side. You can cope with a little bit of loss of transparency. This is what in the jargon we call the transparency between the local side and the master side, no? Always when we are using all these techniques, we are affecting that we are losing a little bit of transparency, but we hope that the human will still feel the difference between being in contact with an object and not being in contact with the object. That is basically what you want to, the feeling that you want to get the operator to, okay, you are holding something.
Okay, but you couldn't, the level of accuracy is such that you wouldn't confuse two different objects. So, you know, you're actually on the real side looking at an object that your digital twin has got wrong. I mean, what I mean? It's a different object.
Yeah, I mean, this is a problem when you have this kind of reactors that you have several parts that are the same. So it's very difficult to actually, if you are only looking to one section of the reactor, when there is a symmetry in the construction,
yeah,
actually it is challenging for the to know exactly where you are, no? So this is a problem that sometimes you need the human to tell the algorithm, okay, you are in this specific part of the reactor. The symmetry is something that is always challenging in this classification, and actually also when you are merging two different set of point cloud, to know exactly which bit are the similar one, because you have a lot of similarities between different components.
Yeah.
Actually, to be able to overlap is always an issue there. And it's something that our colleagues in South Korea are really studying and trying to find techniques to avoid these issues.
Thank you.
No, thank you. Thank you for the question.
Thank you, John. There's another question, Joaquin, from Bio about man-in-the-middle attacks.
We are assuming that Amazon is doing a very good work and is protecting us from these kind of problems. Evidently, it will be a problem when there is when you have a standard or when you have a real problem. Right now, we are more interested in the technicalities of actually transmitting the data to be able to cope with the delays in the. But it's something that in the future, if we arrive to a point of a real practical application, then it's something that it will need to be considered. Right now, we are not considering this issue, but evidently nowadays is something that is everywhere. It's not only with bilateral teleoperation, it's also with controlling pipe of gas and this kind of thing, water, and a lot of issues that so far we have been using the internet almost for everything. Maybe it is trickier or it's something that we need to work harder in projecting this risk or mitigating this risk.
Thank you, Joaquin. If you want, I would say something as well, because I kind of worked on that as well. The architecture used, it's as secure as it can without being designed for security. What I mean is that the VPN approach is encrypted and it has key exchange, although all of that can be broken, but it's included in that architecture. So that can be improved, but right now it's not as insecure as it could be. It could be way more insecure. It could be quite basically just sending data through the internet without either signing encryption but it's built in
previous work that we have done in research. We didn't take care of any kind of security, to be honest. We just open EUP port and send the information and hope that no one is messing around. But evidently, in this work, we are a little bit more concerned about security, and what we are doing is using a VPN of the Amazon web server. I don't know, Han-Lin is also here if you have any further details, because Han-Lin is actually the person doing the work instead of myself of doing nothing. Han-Lin, any additional information?
Actually, we tested the different Amazon server setup, and let me share a video. So we tested 3 different Amazon server. One is the M5, one is M4, one is the free Amazon instance, and we tested the different setup, and this is the control delay of a different setup in this video.
Also,
Yeah, there are other 2 questions.
I mean, so far, I don't think it's been adapted in any nuclear facility. It's still early days for the final adoption. I mean, we will need to go through a lot of different processes until we get it there. We are trying to understand what are the current possibilities of the technology right now, if this is a feasible solution or not, if this can be adapted with the whole bunch of uncertainty that we have currently, is something a little bit in the future, I will assume.
We have another question from Greg about VR teleoperation hand tracking.
Yes. After around maybe 20 minutes, we need to have a rest.
Thank you, Han-Lin. Any other questions, comments? Everyone's happy to. Yes, thank you, Greg.
Another thing that maybe we can comment is that actually we would like to introduce now a haptic glove to provide the force feedback. The tricky bit of the haptic glove is that the current design of the haptic gloves are still difficult to combine with other sensors. So for example, what we are using, the sensor that we are using here is a lip motion. So if you have your bare hand, then the sensor is working very, very well. But as soon as you put something in your fingers, then the sensor is not, it haven't been designed for this kind of application. And I'm trying to find something that combine the force feedback of the haptic glove with a nice control of the fingers and an accurate description of the position of the finger. It's also a challenging question that is still open.
Thank you, Joaquin. Any other questions, comments, maybe also for the first project? We are on time today, so that's been a good session so far. No more questions or comments? Great. Well, we've been very productive then this morning. Would any of the presenters like to say something else before we maybe close the session?
So yeah, I mean, for the Icon Plus project, obviously, I mean, you can kindly contact me if there's any further interest for discussions. Yeah, so I think clearly we have a large team, but maybe it's best actually you contact me if there are any further interests or questions. Okay, thank you very much.
Thank you.
Thank you, Guido. Thank you, Joaquin. And thank you, everyone, for joining us. I think that's it for us today. We'll hope to see you in the next session. Thank you very much. Have a lovely week. Thank you, everyone.
Thank you, everyone.